So what we are going to skip some of the sections. So we're studying tensor products. So maybe so basically so focus mainly on linear algebra. So these one couple of sections maybe we are going to most skip in the first reading because they are part of multilinear algebra. So it has some relations with the linear algebra, but there are some interesting details we are going to leave as of now. But we are going to not jump to, we are going to concentrate on transformations, which will make for us some of the properties of these transformations. There are some things which will allow us to focus on some of the properties which later turned out to be interesting as far as linear transformations are concerned. So before we are going to see the subtleties, so we are going to again define the things. So if we define, how we define a linear transformation or operator A on a vector space V. So a linear transform A on a vector space V is a correspondence that assigns to every vector, not scalar, to every vector. Here is a vector Ax. So we assign to each vector Ax in V, which is a vector space, such that, so this is the way we define. So we'll assign this as like this: alpha Ax plus beta times Ay. So we assign a vector to every this vector. We assign a vector prefix to it. Previously we used to assign a scalar. So here this is the way, in simplest sense, how we define linear transformation. So if you define linear transformations as, for example, or identically in vectors x and y, and scalars are alpha and beta, as it is known. So again, if you remember, if the scalars are 0, so this will come out to be 0. So it will come out to be A of, this is 0, this is 0, this will come out to be A of 0 is equal to 0. So this will make us closer to how we define homogeneous linear equations, whose solution goes like this. And non-homogeneous equation will have some constant, additive constant on the right hand side. So for a particular value of scalars, you should define homogeneous. So if we enumerate the properties of simple properties of linear transformations, we can enumerate them as, for example, so you can always have a number, for example, 0. If you have transformation on that, so it will, that number will define it that way. Or there is an identity element. If it is defined on Z, we'll get the number back. So you can always, these are the simple properties you can enumerate. So in the same way, if the second properties I have not stated it, you can just, it's as simple as that. So if we have x naught be any fixed vector, in V, and y not be any linear functional on V, such that ax is equal to y naught x into x naught, and if we define x in terms of x1, x2, so on and so forth, the arbitrary set of vectors, and y1, y2, so on and so forth, the corresponding set of linear functionals which will correspond to x1. Okay, each x1 there is a corresponding y1 which is multiplied by some operator. So if you see it this way, so you can say ax can be represented by like this, yx22, so on and so forth. So you can just extend this property to n-dimensional vectors or n-dimensional space. And the third property is, for example, if we have a permutation of integers such that 1, 2, and n are integers, and x is equal to, these are scalars, zeta 1, zeta 2, so on, and in the is a vector. Sorry, if x is this is a vector. Sorry, it's not scalar. Vector in Cn, then we can write as ax is equal to pi 1 pi n. So why he has introduced pi? Pi is any polynomial with complex quotient. If x is a vector, so you can have you can associate with it any. You can map it with any zeta, where these are different polynomials. So in the same way, the fourth property which might be interesting is that, for example, if you have any x in Pn of then, for example, then if f x of t is equal to sigma g is equal to 0 to n minus 1 zeta g tg. So if you define now an operator, then operator may be any differentiation of an operator which is acting on that function. So you can define it as b of xt is from j is equal to 0 minus n minus 1. So it will be g will come back. If you simply differentiate it, it will be t of j minus 1. So if you operate it like this, so if you define a function like this, then operator can be defined simply as it will come down. This is it's the derivative of the polynomial. So in the same way, if you want to have a reverse differentiation, is a process of finding derivative of function. The function is given. Integration is a process in which derivative of the function is given, you get the function back. You got my point. So in the same way, those functions, if you take differential as a part of that operator, which is operating on that space, so you define it like that. So if the function is given, you can have a differential of operator is like this. So now if the differential of the operator is given, you can get the function back. So that's it. The fifth property is that if x of t is defined as n minus 1, so we write s of x is, so it's an integral of the function, it's zeta of j, so it will be t of j plus 1 divided by j plus 1. Or for example, if you integrate it t of j, it will be t of j plus 1 in denominator. The integration of x to the power n will be xn plus 1 divided by n plus 1. So it's the same thing. So it's an integral of a function operating on the vector space. This is differential of a function. So you can say it's like xs ds. Now we'll come with some interesting property of vector space. So it will be. So now we define the transformation part of it. How we define transformation in the, how we define linear transformations or transformations as vectors. Transformations as vectors. So again, you can have, for example, if A and B are linear transformations such that their sum S is equal to A plus are defined by the equation S of x is equal to AX plus BX for every x. So we observe that commutative and associative addition. So if it is defined, we can say that commutativity and associativity of the function will give us commutativity and associativity property will be satisfied. Now, where is the problem? Where the problem lies, for example, for simpler properties, it will not be that the results are simple. For example, A of 0 is going to A. So, and if we do have a transformation A on a function, you can also define it like this. There is no problem here. Or A plus B can be 0 if A is defined as B is defined as minus of A. So these properties are simple, but where is the problem? Or, for example, alpha of AX you can define as alpha of AX. And if you follow the book says B and C are immediately verified. B and C, in the sense when we started those vector spaces, those properties which were enumerated as A, B, and C. These set of properties can also be defined and verified for the way we define linear transformations immediately. 1, 2, 3, 4 properties. So they should satisfy taking this A, B, and C combined. So there will be no problem in that sense. And from this, you can have a theorem which says that the set of all linear transformations on a vector space is itself a vector space. So if you have transformations, set of transformations on a, so vector space has to be defined by those operations A, B, and C, which we have the way we define a vector space. So if you have a transformation on a vector space, that will itself be on a vector is itself a vector space. So in though it seems trivial, but you just think over it. Now from this, these set of properties are trivial, or they are sort of intuitive. You can easily relate to them. The thing comes when you define product of these transformations. If there are more than one or more functions, A and B, and have set of linear transformations on them. With the product of transformations, linear transformations will give the same results or not. For example, A into B, if you have linear transformations on A and linear transformations on B, should it give to B of A or not? If you change the order A with B and B with A, should the results, so that's the important thing which we are going to see. So in linear transformations, the commutativity doesn't hold. So in linear transformations, the commutativity, if you change the order of that element on which you are applying linear transformations, the commutativity doesn't hold. So it comes from how we define linear transformations. So for products, this property may not hold. So if we just assume why it should not hold, we can go for a concrete example and then see whether it holds or not, and see the product of the two, and taking one of the operators as one of the operators as a differential of that operator operating on that vector space. So if, for example, if I use the words of book most notorious is a famous in the negative sense, but I will disagree with the way he has said it. I'll say as a physics students, this commutativity is very much useful as a property in the quantum mechanics sense. So it's not negatively famous, it should be positive. Maybe historically it's negatively famous, might be in that sense. But for example, to check it in that sense, for example, if we consider differentiation and multiplication transformation, B and T defined by d of x into t can be written as dx of dt. Now it's an operator which is operating on some function. Now the point is, like, if we have a function like this t of x and t, as if we define it as like t of x of t. Now what we are going to see? We are going to operate first d, then we are going to change the order of d, dxt and then txt. So the order of operator, if there are two functions a and b, we are going to operate first on d by a and b. In the second case, we are going to operate first on b, keeping a. So see what will things arise. For example, b of t into x of t will be equal to, this is on operator. This is operator operating on this. This is the function. So this is not a vector. This is x of t. So we have, in linear transformation, we have defined t as a vector. So d of dt of t of xt. So what will we get? When we first differentiate with this, it will be x of t plus t dx by dt. Is it fine? Now we are going to operate it now other way around. So this is this. Now we are going to operate t of d of x into t. So it will be t will have this t dx by dt. Is it like it's okay? Now what we are going to see, t of, if you want to check the commutativity, so it will be what, t of dx into t minus t of dx into t, ab minus. So you will see, you subtract this from this, it will be, this will cancel with this, so it will be, is it like that? Or if you just get it x, you will get back, so dt minus td into x is equal to x into, so tt will cancel, it will be x. So it's not 0, it's not coming, it's coming x. So So normally AB minus BA is 0. So if you replace A and B as the linear transformation acting on the operators, so the commutativity of two operators acting upon those vectors, the vector space, from this you can say it will not be always 0. So that's it. Or if x is 1, then you can say tt minus dt is equal to is 1. So now, if you read another sentence of the book, so those who are thinking of linear transformation geometrically can, for example, readily convince themselves. For example, as product of the way we do it in vector algebra, the product of two transformations, it depends upon the origin. If you take orientation one way or the another way, cross product you take it. It's not always A cross B is not equal to B, it's minus B cross C. So if you want to imagine vector spaces in terms of linear transformations as geometrical entities, as the quantities, so you can have some analogy here also. And the other algebraic properties you can have is, or for example, with a notable, this is a notable exception of commutativity. Exception of commutativity. So maybe apart from commutativity, other properties hold, which are, for example, you multiply this with a 0, you will get, or you multiply it by identity element, the order of identity element will not change anything. Or associative property, it's like this. Or A plus B into C, distributive property, it's AB plus BC. So now one of the property he has tried to identify is, for example, A into B plus C into X can be written as A into B plus C into X. So it will be A times, first we would be B into X plus C into X. Then it will be A into Bx plus A into Cx. Then it will be AB into X plus AC into X. Or we'll just write it like this, AB plus AC into X. So this is a simple way. First we took B plus C into X. This X is operating on B is X and C in X. Then we close the brackets, Now A, B into X. So we can show it in that simple form. For the case of polynomials, for example, for the case of binomials, AB is equal to BA. So it might have some problems. AB is equal to BE. For linear transformations, the commutativity may not always be there. It will not be always 0. But sometimes it can be 0. Sometimes we can construct, so that is a part of exercise, where commutativity is 0 in a simple sense. You can just you can define this function in such a way that the product of these, the commutativity or product of AB minus BA is equal. You can construct that also. But in linear transformation, you can say it will not always be 0. That is the point. But now, if you want to extend this entire thing to these are non-binomials, binomials, or polynomial functions. Polynomial functions in the sense of P is equal to alpha naught 1, alpha 1A, so on and so forth. And see whether the commutativity holds or not. So maybe if you read the passage of the book, for example, if commutativity holds, this is another property. If commutativity holds means AB is equal to BB. So we know it's not holding always in linear transformation. If it holds for so it may hold in, if it holds in one variables, it's a property. It will hold in n variables. So so you can say the correspondence. So he's omitting a little bit details. So you can just take it as an exercise, as a proof. If commutativity holds in linear transformation, not necessarily if it doesn't hold. If it holds, so if it's true in one dimension, it's true in all. It's also. And the other thing which may come out to be an interesting detail, which I'll just stop. So is that, for example, product of two transformations. Product of two transformations may vanish, even though individually they may not vanish. So individually, the transformation, they are not, the value of the transformation is not zero. For example, AB minus. So individually, product of two transformations. Individually, these A and B are not zeros. But once you, as a product, they will come out to be zero. So that's the point. So once you have linear operations on them, on one of them, that operation will lead to a quantity called zero. It will lead the product to zero. So individually, the vector space is not zero the way we have defined it. The linear transformation makes one of them zero, and that product will make it the other. And the sum in totality, it will become zero. This is also some non-trivial property you can think of if you want. If I'll state it in that sense, if I'll state it in that sense, that a non-zero transformation whose product with some non-zero transformation is called also division of zero. Why it's called division of zero? Divisor of zero. So I just leave it to you. Why it's called. So the book. So you can define a non-zero transformation whose product with some non-zero transformation. This is what I'm saying. Whose product with non-zero transformation is zero. So the divisor of zero. Yes. Because why it's divisor of zero? For example, AB is equal to zero. If there are linear transformations, you can always divide this by this. It will be. That's why it's probably called divisor by zero. What my point? So these are linear transformations in that general sense we have talked today. So we're going to extend on it in the next class. Stop.